Hi, and welcome to this lesson on radiation from antennas. And first I must note that the title graphic for this series of lessons is a picture of the VLA, which is a radio telescope and which does not transmit. So, this image is perhaps not the best choice for a title slide for a lesson on radiation from antennas. Just thought I would point that out. What this lesson is about is characterizing the radiation from antennas. In this lesson, we want to get specific about some of the relevant properties of the antenna. We want to do this in a way that facilitates calculations relevant to radio link engineering and spectrum management. We'll begin with a reminder of how spatial power density works in the far field of a source. Again, this is something that was introduced in another lesson. Then I'll introduce the concept of directivity, which is a handy description of how a particular antenna distributes the power that it radiates into the far field. This will lead to the concept of gain, which is simply directivity corrected for loss, and pattern, which is simply directivity expressed as a function of direction. Finally, I'll show you how to compute the spatial power density radiated by an antenna at any distance and in any direction, and all we'll need to know is the transmit power and the gain. Let's start with an antenna. Now this lesson applies to any transmitting antenna, but in this case I just happen to be showing a picture of a weather radar. The antenna is inside that dome located at the top of the tower. This antenna radiates a total power of P sub t watts into the far field. And what I mean by that is that if we were to go out into the far field and gather up all the power that's radiated by this antenna and add it all up, the sum would be P sub t. We know from a previous lesson that once you get sufficiently far from a transmitting antenna, and presuming there are no reflections or other things going on to disturb the propagating wave, the resulting wave will be spherical. That is, surfaces of constant phase will be concentric spheres centered on the antenna. How if we observe the wave at any point in the far field, what we see looks like a plane wave. The term we used previously was globally spherical but locally planar. And the power density at this point in the far field is something we're interested in. We'll call this power density capital S, and recall that the units are watts per square meter. Now, for weather radar, or essentially any other application, you probably want S to be very strong in one direction and relatively weak in all other directions. So let's keep track of the position at which we measure S. We'll label that position in spherical coordinates. The spherical coordinate r is distance from the antenna, whereas the spherical coordinates theta and phi give the direction from the antenna to the point at which we measure the power density. So, we have capital S as a function of the distance, r, and the direction, theta and phi. Now, the question is, how do we get the power density, S? Perhaps it is obvious that S is proportional to the total radiated power, P sub t. But other than that, how do we get from P sub t to S? To answer this question, let us first consider the simplest possible antenna. This antenna is known as the isotropic antenna. An isotropic antenna is one which radiates power uniformly in all directions. So, the first thing I must say is that the isotropic antenna does not exist in practice. No physical antenna can radiate power uniformly in all directions. The reason for this is that the source of the wave is ultimately current, and current has direction. And since current has direction, the resulting electromagnetic fields cannot possibly be uniform in all directions. To be perfectly clear, we can always have a spherical wave, that is, phase uniformly distributed in direction. The problem is that we can't have power uniformly distributed in direction. So, a reasonable question at this point is why consider an antenna that can't possibly exist? The reason for this is that this is the simplest possible way to distribute power into the far field, and so this concept is useful as a benchmark against which to compare other antennas. As a benchmark, the concept of an isotropic antenna, which distributes power uniformly into the far field, is very useful, as we shall soon see. So if this antenna is isotropic, and therefore distributing power uniformly into the far field, we can compute power density. In this case, we have that the power density is simply the total power that was radiated divided by the area through which it radiates. And if we're located at a distance r from the antenna, then the area through which the power radiates is the area of a sphere of radius r. and that area is equal to 4 pi r squared. So, it's easy to calculate the power density for an isotropic antenna. It's simply P sub t divided by 4 pi r squared. Of course, we want to be able to do this calculation also for antennas which are not isotropic, which of course is all of them. To do this, we need some metric that tells us how the antenna is different from an isotropic antenna. That metric is called directivity. Directivity is defined as shown here. It is simply the power density at whatever point we're interested in, divided by the power density averaged over all points that are at the same distance from the antenna. Mathematically, we can say that this is S as a function of r, theta, phi in the numerator, and then the same thing in the denominator, but averaged over all possible values of theta and phi. So I'm using those angle brackets to denote averaging with respect to the subscript. And we call the result directivity. And we give this the symbol d, and we note that d is a function of theta and phi. Now, we stand back and look at this, and we see that directivity is simply telling us how much greater or smaller the power density is at our location relative to the average power density at the same distance from the antenna. Now, I've indicated on the left that directivity is a function of direction, but not a function of distance r. So you might ask why it is that directivity is not a function of r. Well, this is because we know that we're dealing with a spherical wave. For a spherical wave, power density is proportional to 1 over r squared. That's the inverse square law, and in fact we invoked that principle in the previous slide. This means that the numerator is proportional to 1 over r squared for sure, but the denominator is also proportional to 1 over r squared, and for the same value of r. So these factors of 1 over r squared cancel out. As a result, directivity is independent of r. Now take a moment to savor that result. This means that directivity depends only on direction and not on distance, and that's precisely what we want in a metric that describes an antenna. Another consequence of our definition of directivity is that the directivity of an isotropic antenna, if we could make one, would be 1. And this is because, as we found in the previous slide, the power density at any position is equal to the average power density at the same distance. Denominator equals numerator, so we end up with directivity equal to 1 for an isotropic antenna. The third thing I want to point out is that our definition of directivity results in a unitless quantity. From the definition at the top of the slide, you can see directivity is watts per meter squared divided by watts per meter squared, which is unitless. Another way of saying this is that directivity is a measurement of how much more power density the antenna is delivering than an isotropic antenna if it radiated the same amount of power. Because directivity can vary over many orders of magnitude, it's convenient to express it in decibels. And here that's 10 times log base 10 of the linear quantity. When we do this, it's customary to express the units not in decibels, that is dB, but rather as dBi, which stands for decibels relative to isotropic. So, for example, the directivity of 1 is 0 dBi, meaning the power density will be 0 dB relative to what we would have gotten with an isotropic antenna. Now, let's consider what to expect when we calculate directivity for physically realizable antennas. The first thing is that we will never see directivity be constant with direction. The second thing is that the maximum directivity of a physically realizable antenna will always be greater than 1, that is, greater than 0 dBi. Also, the minimum directivity of a physically realizable antenna will always be less than 1, that is, less than 0 dBi. In fact, the minimum directivity of an antenna could be 0. We refer to that condition as a null. Because the directivity of practical antennas varies with direction, and since we are often interested in the directivity in the direction which is maximum, you would think that we have a term for that, and we do not. What usually happens instead is that someone will simply say that the directivity is some value, meaning that the stated value is the maximum directivity. Now, this can create confusion if you're also interested in the directivity in other directions. Nevertheless, this is the way it is. Summarizing, if someone tells you the directivity of an antenna is a specific value, then they probably mean that that value is the maximum directivity of the antenna. For practical antennas, directivity is a function of direction and will therefore vary as a function of theta and/or phi. We refer to this particular functional variation as the pattern of the antenna. And I'll show you an example of a pattern a bit later in this lesson. Yet another thing you need to know about practical antennas is that they always have some loss. Now, in this case, what I mean by loss is that some fraction of the power that's delivered to the antenna by the transmitter is lost in the antenna and doesn't get radiated. Now, there's lots of ways that loss can appear in a transmitting antenna. For example, perhaps the metal that's used to make up the antenna is not perfectly conducting, and then we have ohmic loss. For this reason, it's often useful to define gain of an antenna as its directivity times a factor that will be less than 1 that accounts for this loss. So for example, if 1/2 of the power that you would apply to the antenna is dissipated in ohmic losses in the antenna and never gets radiated, then you would say the gain is 1/2 of the directivity. Or equivalently, you would say that the gain is equal to the directivity minus 3 dB. Now, just to be perfectly clear, the antenna is not an amplifier. An antenna cannot radiate more power than is provided to it. When we refer to the gain of an antenna, we mean simply directivity times loss. The gain that we're referring to in this case is simply the advantage in power density over what we would get from a lossless isotropic antenna that has provided the same amount of power. Okay, how about an example? Probably the simplest antenna that is actually realizable is the dipole antenna. That's simply a straight wire that's connected to a transmitter via terminals located somewhere along the length of that wire. Now, if that wire is much, much shorter than a wavelength, then we have what is called an electrically short dipole, abbreviated here as ESD. Here, the black curve is the pattern of an ESD, which is aligned along the z-axis. In other words, the wire is electrically short and pointing up and down. The pattern you then see is this dumbbell shape. Note that you have a null straight up and a null straight down. What is the directivity in these directions? Well, it's 0 because they're nulls. What's usually of interest is the maximum directivity, which is achieved broadside to the dipole. For an ESD, we find that the maximum directivity is 1.5, which means 1.5 times greater power density than we would have gotten from an isotropic antenna given the same amount of power. And 1.5 in linear units is 1.76 dBi. The blue curve shows the result for a half-wave dipole, abbreviated HWD here. The half-wave dipole is identical in all respects to the ESD, except it's longer. Specifically, its length is equal to 1/2 of one wavelength. As a result, the half-wave dipole has greater directivity than the ESD. Specifically, we see the maximum directivity has increased from 1.5 to 1.64, which is 2.15 dBi. Also worth noting here is that the consequence of increasing directivity is that the overall width of the useful part of the pattern is narrower. This trend is general. In fact, the higher the directivity, the narrower the range of directions over which a useful fraction of the power can be delivered. In the previous slide, we examined only the pattern in one particular plane, namely a plane containing the z-axis. In this slide, we're looking at the pattern in a plane containing the x and y axes. That's the one shown on the right. In this plane, the pattern is uniform. That is, power density is constant with respect to phi. This should not be surprising since the dipole has perfect radial symmetry in this plane. When we have a pattern which is uniform in one plane, we refer to the overall pattern as being omnidirectional. Now, this is another place where terminology can get confusing. Omnidirectional does not mean isotropic. Isotropic means uniform in every plane, whereas omnidirectional, in the sense that antenna engineers use this term, means uniform only in one plane. The origin of the term comes from the use of vertical dipoles for terrestrial radio applications, where all the receivers and transmitters are essentially in the same plane. And in that case, the term omnidirectional is a bit more intuitive. But there you have it. Some antennas are capable of very high directivity. For example, the weather radar we mentioned earlier in the lesson would certainly have a very high directivity. probably 20 dBi, maybe 30 dBi, maybe more. The pattern of such an antenna usually looks something like what I've shown here. To the right, we have a main lobe, which is where the greatest directivity happens. Because directivity is high, the main lobe is narrow. So, it becomes useful to quantify the width of the main lobe. The usual way to do this is using the metric of half power beam width, abbreviated HPBW. HPBW is usually defined to be the angle shown here, between the points at which the directivity is 3 dB less than the maximum directivity. High directivity antennas also tend to have lots of side lobes, with nulls between the side lobes. Side lobes of particular interest might be the first side lobes, that is, the ones adjacent to the main lobe, and the back lobe, which is a lobe that points in the direction opposite the main lobe. So now we've come full circle. We want to know the power density at a certain distance r from this antenna and in the direction theta phi, which may or may not be the direction of greatest directivity. The things we know about the antenna are the power applied to the antenna and the gain of the antenna. Now, as a reminder, if this antenna were isotropic and lossless, we know the answer would be simply total power divided by 4 pi r squared. We worked that out before. But now we know the power density will be greater by the gain. So, the actual power density in this case will be gain times power applied divided by 4 pi r squared. And that's all there is to it. So now you know how to compute the power density at any point around a radiating antenna. Okay, time to review. Directivity is the key idea in this lesson. Directivity is the power density in a specified direction relative to the power density averaged over all directions. Equivalently, you could say directivity is the power density in a specified direction relative to the power density from an isotropic antenna that's radiating the same amount of power. And keep in mind, when we say directivity, sometimes we just mean the maximum directivity. That you have to figure out from context. We talked about the gain of an antenna, which is simply directivity times loss. If the loss internal to the antenna is negligible, then gain and directivity are essentially the same thing. We now have a recipe for computing the power density for the wave radiated by the antenna. This power density is simply gain times total power divided by 4 pi r squared. And to wrap up, 2 additional comments. First, note that we have completely ignored the issue of polarization. In other words, we've assumed that whatever device is measuring the power density is copolarized with the wave. To the extent that this might not be true, well then of course the relevant measured power density will be less. Finally, perhaps you already know that the directivity of an antenna can also be used as a metric of receive performance. This is true, but a discussion of that idea will have to wait for another lesson. That concludes this lesson on radiation from antennas. Thanks for listening.